Hello friends, welcome to our channel. In this video, we are going to look at problem 3419, minimize the maximum edge width of a graph. So in this video, we are going to explain a solution based on Dijkstra algorithm. So let me make some annotation. So in other words, I'm going to do this problem using slightly different method than that given by the hint, right? So let's first quickly look at the problem statement. So basically, we have a directed graph, and with n nodes, the nodes are indexed as 0 to n-1. And the graph is represented by 2D integer array, right? So AI, BI, WI means that there is a directed graph from AI towards BI with weight WI. So our goal is to remove some or zero edges from this graph so that it satisfies the following conditions. First, node 0 must be reachable from all other nodes. So in other words, node 0 is a sink, right? Node 0 is a sink. And the second one is the maximum edge width in the resulting graph is minimized. So this is actually the key point for this problem. So we are going to translate or change this statement. So the problem is how to do reduction of problem, or we can say transformation of the problem. This is actually very important, but the key point is given by this sentence. So also each node has at most threshold outgoing edges. Actually, it turns out this is not very essential. So here we are going to return the minimum possible values of the maximum edge width after removing the necessary edges. If it's not possible for all the conditions to be satisfied, so we're going to return -1, right? So that's actually the problem statement. So here, actually, you need to pay attention to this. So there might be multi-edges between a pair of nodes, but they must have unique weights. Because of this, basically, we want to choose the smallest one among this one, right? So with that said, let's quickly look at one example. So the first example, you can delete this edge. So you basically, you will get the maximum which will be 1. And in the third one, actually, you can check 1, 3, and 1, 4 to be removed, and 1, 3 and 1, 4 to be removed. Then the maximum will be 2, right? In example 2 and 4, it's impossible, so we're going to return -1. So with that said, let's look at the problem. So we know that for Dijkstra's algorithm is a single source shortest distance problem algorithm, right? So basically in this algorithm, there are two ingredients. So one is a heap data structure, right? So of course it involves some dictionary or list. You can monitor the distance and the parents. So we're not going to emphasize that. Another one is relaxation, right? Relaxation. Basically, for example, arriving at a current node has a distance u, and then from distance u you have to v you have a weight. If this is less than, right? So the distance v. So dv means, or du means the shortest distance from the source to u and v. So then if we by v of u to arrive v is less than this one, then what we're going to do, we set dv equals this one. This is the relaxation, and this is the two core parts of the Dijkstra's algorithm. But here, how do we do this? Because first we want the 0 be reachable. then we can actually consider the reverse graph, right? Here by reverse graph, it means if in the original statement you have a edge from U to V with weight W, and then actually we are going to build the graph from V to U, right? And then still with weight W. Then here node 0 must be reachable from all other nodes, can be translated to if we use 0 as source, and then it can reach all the other nodes. So that's the translation or reduction of this part. And then how to do reduction and transformation for this one. So the maximum edge weight in the graph. So in the original one, in Dijkstra's algorithm, you do this, right? But here, what we want to do is the maximum edge weight in the resulting graph is minimized. So in each pass, if you look at this each pass, for example, in this pass you have some weight W1, W2, and Wn, right? Then in this case, we define the distance of this pass, or every node in this pass to the source will be the max of this W1 up to Wn, right? So if we can, we can interpret or compare this one as the distance to nodes in the path, or the minimal distance to reach all nodes in the path. Then this actually translates this problem into a Dijkstra's algorithm problem. So I guess up to now you might have some confusion. Now let's look at the code. Actually, the code is rather short and straightforward. And once you look at the code, I guess you can come back to this statement and then try to digest this part and this part, especially this part. I guess very, very relevant to the Dijkstra's algorithm. In other words, when we look at the relaxation, we do not do this du plus duv. Rather, we consider du at the maximum of this one. So this one is translated to, so du, and let's assume this w is just this one, right? So we consider this one. If this one is less than dv, so we are going to replace dv to be max du w. In other words, the format of relaxation is adapted to the problem here. So with that said, let's look at the coding. I'm going to build graph collections default dict. So actually you can either use list or set, both are okay, right? Then we are going to traverse this graph for x, y, and w in edges. So this in the original graph, it means that I have a graph pointing from x to y with weight w. Because we consider the reverse graph. In this reverse graph, so what we get, we actually do from y to x with weight w, right? So what we do is graph y. So this is the starting node. It means that x is in the neighborhood of y. But I want to store two pieces of information, also with this w, right? And then we can run Dijkstra's algorithm. So this one is build the reverse graph. This is a very standard, right? So now let's look at the Dijkstra's algorithm. For this, we need to have a heap and a distance dictionary or list to monitor the distances. So originally we set them to be infinity, right? So here we have an n. N is the number of nodes. So basically for in range m, right? So because the source will be 0, because we reversed the graph, and then we can from the source node 0, we can traverse to all the other points. So we can see dist and 0 to be 0. And then we want to have a heap, right? So the heap will be something like this. So we want to store two pieces of information. First, the distance of the from the source to the node, and then so the node itself, the current node. So basically, what we have is the distance and the node. So here the distance is different from the one we typically understand. So this distance is that if you want to reach from the source to the current node, and then along the path, the maximum weight, that will be the distance, right? So it's good to put a quotation mark, right? So you will see the relaxation, and then this point will be very clear. So while heap, so what we can do, so we can get the distance, and we can get the node. So basically it's heap q, heap pop, right, from this heap. So this is the current smallest edge or distance, right? So what we can do, so we can check the neighbor of this this node. So for, let me right here, for yw in graph x, notice that here we are using this yw as this graph x is a list, right? Contains the tuples of yw. And then what we want to do is to do relaxation. So what we want to do is to check the current distance will be the max between, so previously the d and the current w, right? Then if current distance is less than d of y, right? So then we are going to do d of y to be the current distance. So this part constitutes the relaxation, and then you can compare with here, right? So that's what we do. So that's actually the relaxation tailored to the current problem, right? So once you have this, basically you are done quite a lot. And then what we are going to do, because we need to include the current information, heap push. We want to push this y and this the distance. So let's call it dy, and then this y, right? So then after this, what we want to do is we want to compute the max. So let's call it m. So it's a max of dist, right? So if the capital M is still positive infinity, it means that this condition cannot be satisfied. So we should return -1. Otherwise, so this M will give us the information as the title specified, the minimum of the maximum edge weight on the graph. So what we want to return is return -1 if M equals flow to infinity. Otherwise, so we're going to return the capital M. So that's the main problem logic. So let's first do a test. So integer object is not subscribe. So let's see. Let me check that. If current d is less than d of y, so I didn't write d as here is dist, right? Still, I need to change this to be dist. So let's see if I change it all, right? Yes, so this is dist. Heap q, heap pop, max, heap q, heap push. I need to heap push into the heap, right? This information. Now let's run it. So it passes all the cases. Now let's look at the generic case. Yeah, it passes all the cases. So I guess that's basically about it for the current problem. Let me come back to the very beginning and give a quick summary. So here we use Dijkstra's algorithm to solve this problem. And we actually used two tricks. First, we consider the reverse graph. so that we can do traversal essentially from 0 to all the other nodes. And so this is embodied by the Dijkstra's algorithm traversal, right? So here, the second part, the maximum edge weight in the resulting graph is minimized. So we translate this into a different distance representation. So here, distance with quotation mark, right? So we embody this by the specific relaxation we used tailored to this problem. So with these two pieces of tricks, we can do this problem very efficiently. So actually, if you look at the description, so here that's some hint. So actually, we can use binary search. So that's actually also a very good technique. So in fact, in our playlist for binary search, we have gathered a lot of problems on how to use binary search. So you can check those. So you can also check the graph algorithms in our channel for more practices. So with that said, I guess that's about it for the current video. Thank you for watching.